Correct. They don't say anything about u. U is free. So u, having seen the matrix, wants to be 1. So there you go. U equals 1. Actually, you don't really want to be the 1 if you're in the matrix, do you? It's kind of an unpleasant existence. I might rather be like, I don't know, some other character, I think. Let's see here. Yeah, u equals 1. And so we just get the one solution, x1 of t equals to e to the 3t, 1, 0, 0. And yet the theorem I told you guys last time says we need 3 solutions. What gives? Where's my other 2 solutions at? They're what? Origin. They're at the origin. Or you say ask the oracle? No. Let's see here. No, now here would be a nice intuitive leap for you guys to make that I would respect. You should just be like, well, I would just multiply by t, right? It's a repeated eigenvalue, just like when we had repeated values before, just multiply by t, right? You want this to be true. Is no true, it no work. So sorry, not the solution. It would be nice if that was what it was, but it's not that. So for now, I will leave it a mystery. Unsettling, no?
Have like x2 is like we leave like b free or x3 leave w or something like that, or how does it work?
What's that?
I think like for each case allowing x is 3, we can have one case where u is free like x1, another one where b is free, and another one w is free, or would that not work?
Those wouldn't be eigenvectors, though. But yes, something like that does work, but there's I can't explain it today. I just can explain to you that there's something missing. That much is clear from what we've done. Okay, so let me show you a different problem. So usually, for the most part, I can test what I need to on tests with 2x2 problems. I don't want to rule out a 3x3 problem because I think it's important for you guys to be able to do 3x3 problems. But I have to be careful with 3x3 problems because it's very easy for the characteristic polynomial to get really hard to factor for a 3x3 problem, right? So I have to personally be careful with 3x3 problems. There are a lot of 3x3 problems out there that the cubic polynomial that you have to factor, the characteristic equations, just too difficult for an in-test kind of thing. So I'm just trying to tell you, you could find 3x3 problems in my notes which would be unreasonable for a test, right? But you could find 3x3 problems that would be reasonable for a test. The one we just worked is very much reasonable for the test, right? Well, you don't have to agree with me. All right, this is America. You have the right not to testify against yourself, right? I mean, at least for now. What?
How long do you think it would take to do one of those questions? Like, after we've done the practice then?
This?
Yeah.
10 minutes. 15 maybe. Yeah. Let's see here. So next example. Let's see here. How about 3x minus 2y and y prime equals to 2x plus 3y. I want to show you how to solve this problem. So what's going to happen here is something interesting. So we got ourselves xy prime, and here's 3 minus 2, 2, 3. Like so. All right, so I got to calculate my characteristic values. What do I got? I got myself a determinant, 3 minus lambda minus 2, 2, 3 minus lambda, also known as lambda minus 3 quantity squared plus 4, or maybe better yet, 2 squared. So what does this say? You know it, you just don't want to admit it, right? What's that? Give somebody else a chance. Maya, you look like you have a thought. Oh no, you're thinking too hard. What is lambda equal to? What you were saying leads me to believe that you were thinking lambda is 3 plus or minus 2i, yes? But you were then thinking about this problem we've already worked, which is a different problem, right? That would be for something like, y prime prime minus 6y prime plus 4y equal to 0. This is not that problem, though. This is a system of two differential equations and two unknowns. It has similar algebraic features, but it's different, right? So complex eigenvalues. Cool. Theorem. Check this out. If AU is equal to lambda u, where lambda is equal to alpha plus I beta, and u is equal to a plus ib. This is pretty much the standard notation. So the real part of u is a, the imaginary part of u. Oh, guys, by the way, the last test, there were some unfortunate things that happened in terms of what is an imaginary thing. Imaginary things are real. Sorry. Like, it's an imaginary component. The I is here, but the imaginary part of u is itself a real vector. This is unfortunate terminology. It got you guys on the last test, many of you, right? Because I asked you for a real solution, and you threw away part of the real solution, which was built from the imaginary piece. Right? C1 cosine plus C2 sine. Well, the sine is the imaginary part of the exponential, but it's very much real. Right? You guys weren't like in the middle of calculus 2 and you're like, we should stop doing these integrals of sines because this is a course about real calculus and I'm annoyed that you're talking about this complex sine function. No, you did not do that because sine is real. So, sorry, this was a rather complicated analogy to express my point. But anyway, theorem, then, check it out. A times A minus IB is equal to, believe it or not, alpha minus I beta times A minus IB. Now, usually I just call this thing U star, and usually I just call this thing lambda star. So all I'm really saying is if you have AU equal to lambda U, that implies that AU star is equal to lambda star U star, the complex conjugate. Basically, the thing is A is its own conjugate. A is real. So this is great. This means that if I find a complex eigenvector, the other eigenvalue, the conjugate, it's already there. I just have to complex conjugate my eigenvector. I've already got the other eigenvector. Okay, let's find it. We'll do the plus. So I've got to have A minus 3 plus 2i times the identity matrix, which I'll write out this time. You're like, well, it's about time. Right, fine, you got me. Any question? Okay. So this here is what? What happens? What happens to the A? What's A here? 3 minus 2, 2, 3, right? So the 3's are canceling, right? And so I got myself minus 2i, 2, well, minus 2, 2, and 2i, yeah? You're like, but are those this, I mean, is there, if it's right, then we should find the second and the first equations are the same equation. For a 2 by 2 system, it must be that the two equations are the same equation, or at least one of them 0. If you have two genuinely distinct equations, that means you only get the 0 solution, which means we made a mistake. So it better be the case that my first row and second row are related in some simple way. Can you see how they're related? Like this first one is minus 2iu minus 2v equals to 0, right? If I multiply this equation by what? By I, this gives me minus 2i squared u minus 2iv equals to 0 times I, which is 0. But I squared is minus 1. So this is u minus 2iv equals to 0, which of course is, oh man.
2 over 2u? Wouldn't it be 2u minus 2iv?
Yes. Sorry. 2u minus, or 2u plus 2iv, right? Oh, I'm an idiot. So they just multiply this by I. I'm an idiot. So just multiply that by I, right? Still an idiot. Multiply by minus I, right? So if I multiply this by minus I get minus 2iu, and then minus 2i squared v, which is minus 2v. This is just me doubting our calculation, right? This isn't actually an essential part. You shouldn't count this towards the minutes on the test, Travis. What we're doing right now is not necessary, right? It's like, I'm just trying to give you some pointers on how to know you're wrong. All right, so hopefully that won't happen, right? So let's look at the second equation. We've got 2u plus 2iv equals to 0. So that says that u is equal to minus iv. So I think I'll let v equal to 1. That will make u equal to minus I. Therefore, u is minus I 1. And my solution, x of t, will be e to the 3 plus 2i t times minus I 1. That's the complex solution. We can, what is it? Oh, that's you, right? No? Did I forget what time class ends? Well, right. I mean, it's not like I'm not like 15 minutes over or something, right? I mean, you guys would have left by now. Yeah. You could be a little bit less enthusiastic about the fact that you're hungry. All right, you got me. I'll allow it. So this is a complex solution, right? This is not the one we want. We want real solutions. So what you do is you extract the real and imaginary parts of this, which I'll explain in more detail when we have time. Obviously, not right now, but your general solution is x equal to c1 e to the 3t cosine t 0, 1 minus sine t minus 1, 0 plus c2 e to the 3t sine t 0, 1 plus cosine t minus 1, 0. So just to emphasize what's going on here, this is A, this is the B, this over here is the A, and this is the B. And this is really just coming from expanding the fact that this is e to the 3t cosine t plus, cosine 2t rather. Did I do 2t? Uh-oh. Oh no. I gotta fix this, guys. 2. Sorry. To reiterate what's going on here, when we have a complex eigenvalue, all right, we find the complex eigenvector, and then we just do e to the lambda t times that. Then the thing is, it's a complex solution. We can again prove the theorem that the real and imaginary parts of the solution are separately solutions to the differential equation. And so we form a linear combination of those to get our general solution. Yes, sir?
I might be crazy.
Uh-oh.
No, I think you're right.
Yeah.
Okay,
I
good.
think you're right.
Where you multiply by negative I to go from
Up at the top in your green. Go to the green.
Oh.
Oh, yeah. That, yeah.
Where you multiply by negative I think the result should have been negative 2iu plus 2v.
Yes.
The negatives will.
When you subtract it up at the very top, like not on the top, in the middle of your board, but when you started doing your lambda equals 3 plus 2I, in that first step, the matrix that results is wrong. You need a negative 2I in the bottom right-hand corner.
Okay.
I feel like that changes.
And then, so then you're.
What?
Your two equations are.
Oh, then these right here.
Yeah.
Now explaino? All right.
Now you multiply by just I.
Now, you're multiplying by just
Still-
you would get plus 2b
It's
on
negative
top.
I. Yeah, it's negative I. Negative I is
It's
fine.
negative I.
Because negative I plus negative I is positive I, which is negative 1. So we break.
I tried for a really long time to not say like.
You're fine. There's errors on the board right now, but I hope the big idea is clear from what we did. I'm hoping.
No, I was too stuck on the other side.
You're still stuck on that. Oh my goodness gracious. Oh, you're kidding. Okay. You should realize in my current state of tiredness, I don't always understand humor.